Hey everybody, you guys able to hear me okay? Yes, okay, thanks. Great. All right, well, let's go ahead and get started. We'll start with some course logistics. Oh, I want to mention, I don't have this in the slides, but you have a quiz that's due today, which I had cleverly put in Canvas ahead of time, and it was supposed to release right after our last class. But apparently if you don't click save and publish, even if you set the release date and you just click save, it doesn't publish it for you at a later date. So long story short, if you haven't done the quiz yet that would be due today, it's due at midnight tonight now because of that little mistake, and I will try to use Canvas correctly from now on, although it is more challenging than you might think. Okay, so other announcements. Your full project first revision is due on Sunday by midnight, and so that's just functional prototype, and we're going to use that for peer review. And so you'll get feedback from other people, from another person in the class, and you'll get feedback from me on that. Okay, let's see. Also, assignment 3, the design guidelines assignment, is due next week on Tuesday by midnight. And that's where you just go and look at either one of the design guidelines that's provided in the assignment, or find one from a company or product that you like, and then just answer these 3 quick questions on it. So that's due on Tuesday. Other really important announcement, we'll be doing our in-depth look at prototyping tools on Tuesday in class next week. So if you have specific questions about specific tools, there's an ungraded survey on Canvas that you can fill out and submit that with your questions. So that way I have a little bit more time over the weekend to look into anything that you might want answered and make sure that I know how to answer it for you. So if you haven't done that, I think only like 7 people have submitted it. If you have questions and you haven't done that, please do that by tonight, so that I can be sure to include everything that we need to include during that lecture. Okay. So last time we started talking about analyzing evaluation data. And so we've kind of been in this series looking at how we evaluate interfaces and systems, and how do we design those evaluations, analyze that data, and then present that data. So today we'll talk a little bit more about analyzing data. We'll finish up what we were talking about last time, and then we'll talk about presenting data, and some data visualization we'll talk about briefly. So, analyzing evaluation data. If you remember last time we talked about just statistics in general, this idea of having descriptive statistics that just describe a measurement, correlations relating to measurements, and then being able to compare differences in groups between 2 conditions or 2 systems that you might be evaluating. And how do you do that using a statistical test to tell you that things are different. So we talked about types of data, and I've kind of just re-summarized this into a table for you to make it a little more convenient to reference. But we talked about these different types of data, starting with nominal data or categorical data, which are just groups that have no ordering, something like your eye color. And then moving on to ordinal data, which might be something like ranking something. Or if you've ever seen like a survey where you have it asks someone what their annual income is, and it has like brackets, 10,000 to 30,000, and then 30,000 to 50,000. So when you kind of bucket things like that, that usually falls into ordinal data because it has some ranking, but it's not necessarily a meaningful interval between it, depending on how you group things and how you divide them out. And then we talked about continuous data in either interval or ratio form, and that's data that we can do math on. It's a continuous number. If it's interval, there's no natural 0 point, and if it's ratio, there is. And then finally, of course, we have qualitative data, which is any kind of data that's non-numeric. Things like interview questions where you ask somebody what their experience was like, or how they felt, or how they would describe something, or just open-ended response questions. So when we think about describing a set of measurements, we typically want to think about distributions rather than thinking about just a composite value. So I've got a graph here, and this is mobility data for Oktibbeha County. And it's a histogram. So across the bottom are the different, that's in kilometers, different distances of travel. And then this is just a frequency of how, each day there's a measurement for the average, kilometers traveled for people in this county. And this is just graphing the frequency of those. And so you can kind of see here, so this is data from the beginning of March up until about a couple of days ago. And this is collected by a company called Descriptives Labs, and they use mobile devices. So there are a lot of apps that people have installed on their mobile devices, and a lot of them include tracking, location tracking, which gets shared with third parties. And what they've done is made this data publicly available for all the different counties in the United States. And they did this as part of a response to COVID and looking at people's mobility, trying to see when travel increased or decreased. And so they've been publishing this data daily since March 1st for every county in the US. And it's incredibly interesting to analyze. So this is just a really simple histogram of it. I did this in Google Sheets. I'll show you some more of it, not today, but probably in another lecture, and kind of show you what you can gather from this data. The name of the company, it's Descriptives Labs. Let me see if I can. It's a GitHub. Let's see. I'm gonna pull it up real quick. Okay, let's see. There we go. So yeah, this is their GitHub where they publish this. It's usually 24 to 48 hours behind, but they've got it in a variety of formats, and then they've got some description here about the data. And then there's even some visualizations here that you can see that other people have done. So definitely a really, really fun data source to look at. And it's really interesting that we have that right now. But getting back to looking at this set of measurements. So when you look at kind of this histogram of it, you get an idea, and you can see here almost that there's really, let's see, kind of two peaks in this data. So a normal distribution would just be, this one curve, but here we kind of see there's two. And if I divided this and got more resolution on it, then we would see other trends. And obviously I'm combining all these days, and so if you start to look at data about how people travel around, you'll quickly realize that it depends on the day of the week, right? So work weekdays versus weekends, there are differences there. One really interesting thing about a county like Oktibbeha County is that it has a large university located in it. And so you see kind of these incredible variations that you don't see in other places when students return or when they leave. Another interesting thing is if you look at counties that were recently affected by hurricanes, kind of hitting the Gulf Coast of the United States, you can see the people leaving the area, evacuating in the data very clearly. So it's just one of those sets of data that's really interesting to take a look at. So obviously you could average things, you could look at the median. The way that they actually compute this, the daily value of travel is a median. So it's kind of a median of medians. So they have however many devices in that county, and then they arrange them in order, and then they take the median value. And they've got a bigger description of that in the data source if you want to know more about their methodology. But the point is, and you can see here, like we've got this outlying case right here, where we had a lot of travel. And my guess is that this is probably right before spring break last spring semester. So that day had a huge amount of traffic with people leaving. But you can see if we were to average all of this, we would get a value that might not represent really what's going on. So the important thing is taking a look at a distribution. So I want to give you some examples of things that are that you might do in evaluating your interface or a product or something. And this comes from the interaction design book. And this is an example where they had, it's a hypothetical example, I should say, talking about, if you had somebody evaluating two smartphone designs. And so they've got these semantic differential scales here, right? So you've got, kind of opposites on each side, so annoying and pleasing, secure and not secure. And you're going to just have the participant interact with the device and then, mark on each one kind of where they feel the device goes. And so in the book, they provide kind of a data set. So we've got two phones here. And what they've done is just counted the frequencies of, so looking at this like annoying and pleasing of all the participants they ran, which I think was 100 participants in this hypothetical. How many people put a 5? So there's 12 people there. And how many did, 4? And he did it for each of these phones. So that's nice, but my animation will go. There we go. It's actually, a little more intuitive to look at this graphically. So you have this big table of numbers, but you just want to run some descriptive statistics, right? So I'm looking at, we're just looking at the entry for the line that's called modern or dated, this last one at the bottom here. And so they've just plotted out, how many respondents evaluated as a 1. And so phone 1 they've put in this color and phone 2 in this color. And so you get an idea of kind of the evaluation of these two different phones. And where the distribution lies, and they're very different. Whereas if you just look at the average here, you do get the idea that phone 2 is leaning more towards the dated side, which I should say is kind of counterintuitive to think about, and you've got to be careful when you have multiple items, because you might think that like a higher number is better, like more modern, but in this case, their higher number was dated. So we see that phone 2 is coming out more dated. And that's just a really simple visualization that you can do in any kind of spreadsheet software or anything like that. So if we move a little bit further and we want to start making comparisons, right? What becomes important is we want to make an estimate of what kind of the truth is in the world. So we're not going to be able to go have every person evaluate our two phones. But we'll have a sample, right? We'll have some number of people that will do that, and we want to use that sample, and we'll come up with a range to say, that if we looked at the full population, the true value lies between this number and that number. And so think about this as just, like if we're rating how modern the phone is, right? We'll get some average value from our participants. But we want to know what that, we want to say with some confidence what it would be in the general population, which we haven't measured. And so the way we do that is we create a confidence interval. So confidence interval is about trying to find that range for the true population. So probably the most common example is a 95% confidence interval. And that just means that we're going to calculate it such that there's only a 5% chance that the true value is not within that range that we come up with. And so to calculate a confidence interval, today just use software or a computer, but it's not that bad of an equation if you want to do it. But it just takes into account the sample size, how many points did you measure, the standard deviation of those measurements, and then the level of confidence. Do you want a 95%, a 90%, a 99%? And that's how you compute that, and you end up with two numbers to show that range. And I just pulled a really simple example. I don't know, this is probably from something for like 4th graders or something, but mathisfun.com. And this just gives you a really kind of a clear picture of what a confidence interval is. And so in this case, they're measuring heights. And so they've measured 40 men, and they're doing the reason they're choosing a specific sex in this case is because there are variations based on that. And so then they're using their samples to calculate this interval to say that 95% of the time people are going to fall within this range. So a really simple example, but useful. And if you want to calculate a confidence interval in some spreadsheet software, this is from the Measuring User Experience book. So this is how you would do it in Excel. And the formulas are similar in Google Sheets or in Apple Numbers or whatever you're using. And you can see it's really quite simple here to calculate the confidence interval. In this case, the value that it's giving here, I believe, is the plus or minus range that you would have. And so we looked at this last time. So a lot of times you'll see error bars representing a confidence interval, kind of showing what we are confident in, our measurements. So in this case, the thing we measured is right here at the top of these blue bigger bars, right? But because we're not entirely certain if we want that confidence range, we include these error bars to say, well, really it's somewhere in between these. And so when you put measurements next to each other, like design A and B here, and you see that this error bar and this error bar do not overlap at all, that's a significant difference between those two groups. Now, if the error bars overlapped, either entirely or partially, typically then it's questionable if there is a statistically significant difference between the two things you're measuring. And so it's a quick visual way to see that. So talking a little bit more about the actual statistical test that you might run. So we have parametric and non-parametric tests. And so the parametric tests are things that we do for any of those measurements like interval or ratio, numbers that we can do math on. So things we can add up, we can take averages, means, an average is a mean, means, medians. And an important thing to note when we do a statistical test, a parametric test, is that we assume that our data meets some assumptions, some pretty important assumptions, and one of them being that the data fits a normal distribution. And there are tests you can run to find out if that's the case or not. But a lot of our inferential statistics are based on meeting that normal distribution. So the simplest example of this is students' t-test, and that will just compare two distributions. And I'll show you that in just a moment. Now, on the other side, if we've got data that's non-parametric, or if we've got data that's categorical, not interval, something we can't do math on, things like frequencies or counts, we use non-parametric test. And so for a non-parametric test, the data doesn't have to meet that normal distribution assumption. And the example that we talked about last time was a chi-square test, which is a really commonly used one. So to show you, again, just in Excel or any spreadsheet software, if you want to do a simple t-test, this is the syntax right here. Not bad at all. So you've got two things you're comparing. Now remember, it depends if we are comparing things in a within or a between subjects design, right? So if you're doing between subjects, that means each person only evaluated one version or one condition of the thing they were evaluating. And if it's within, then each person evaluated each of the versions or conditions. And so it's a slightly different calculation, so you just need to know that. So when it's a between subjects design and one user sees one system and evaluates it, we consider that to be an independent sample. And so we can conduct a t-test with independent samples. And so we get a value here, a p-value, and that's just indicating the probability that the differences in the two data sets could have happened by chance. So if we get, like in this case, 0.047, right? So there's a 4.7% chance that just by probability, these two are actually the same. There's actually no difference between them. In HCI research literature and a lot of scientific literature, kind of the magic value is 0.05 for a p-value. That's kind of when things are considered, a significant outcome. Oh, can I explain the equation circled for A14? Yeah. So in this case, this is just an Excel function for t-test. And so it looks like it's got, let's see, 1, 2, 3, 4 different parameters here. And so the first one is this set of values here. The second one is the other set of values. And then we've got two other parameters here. They're both 2. I'm not entirely sure what they are off the top of my head. I'm sure Excel will tell us. We'll see if I can find out real quick. I'm curious. Oh, here we go. Oh, okay, that is interesting. So it looks like the first one is the first set of data, array 1, and then the second one is array 2. And then the parameter is a number of tails. So we haven't talked about this, but it's looking at if you're coming from both sides of the distribution. So when we have a distribution, let me see if I can just jump over here and show you real quick. Okay, so like this distribution that we looked at earlier, right? If I drew a curve on it, you would have a tail on this side and a tail on that side. If we're making a comparison where we know the directionality of something that we're expecting, we only have to do a one-tail test. But typically we will do a 2 tails test. And so that's what that second parameter of that 2 is. Now that third parameter is the number of tails. The fourth one is the type. And so you can see here they've got the types listed. And so in our case it was a 2, which is 2 sample equal variance. So that's the independent samples, right? Get free expert help with your math homework. Interesting. Okay, so I don't have a ad block here, I guess. So if you're looking at the independent samples, then you would have a 2, whereas if it's the paired samples, I bet it's going to be a 1. We're going to look at that next, so let's see if that holds up. Okay. So, yeah, look at that. It's a 1. Huh. Okay. The documentation is correct. It's a good question. And there's a ton of resources in terms of using Excel or Google Sheets or whatever if you want to do basic stats. Really easy to do this these days, which is nice. Can't imagine when people had to do this by hand. But anyways, so here's an example of using paired samples this time. And so this is when the same user evaluates both of them. And so that changes how things are computed. But we kind of get the same outcome here to decide if they're significantly different or not. So I'll give you a quick example of a non-parametric test, which is the chi-square test. And this is about, it can get a little more complicated than this, but this is a really basic version. It's about making observations and comparing that to what you would expect to happen. So comparing observed values and expected values, and kind of determining the likelihood that something happened by chance by doing that. So this is how you can do that in Excel with a simple table. There are lots of other variations on this as you actually design something that typically things are more complicated than this simple version. But very useful for that. So, and we'll move on to correlations, which is something that I think we're pretty familiar with just in general. And it's just the idea of relating two variables, right? So in this case, we have an example where we've plotted out record sales here versus amount spent on advertising. And we fit a linear line to it, and we kind of get that trend. And you see all the points are all just out here, right? You could fit nonlinear functions to these points too. And certainly at its core, a lot of inferential statistics is fitting linear models. And it takes a little bit of work to get down to that level to see that everything is kind of doing the same thing, fitting these models. But when you're using inferential statistics, all you're doing is fitting linear models. And if you want to go outside of that, then you can look at things like Bayesian statistics and other approaches that also are helpful. And especially also if you think about things like different machine learning algorithms and the way that they fit data, they're not so constrained to some of these approaches. But in terms of studies and the social sciences and just evaluations, we typically use just these inferential statistics to evaluate things. Important thing to remember, correlation doesn't imply causation. There could be a lot of reasons for that. So I could just give you this example. I really enjoy this website, so if you should check this website out. It's got spurious correlations. And so it's just got a lot of examples of things that correlate, but obviously probably not in a meaningful way. So in this case, we're looking at the divorce rate in Maine and the per capita consumption of margarine. Probably not related, but as you can see, they correlate pretty well. So you can't just blindly do math on these things and find anything that correlates and say that's meaningful necessarily. So yeah, it's pretty funny. There are a lot of them. I think the person who made this website also published a book of a bunch of them, the best ones. But so you get things like that, and that's just to say that you kind of gotta use your common sense when you're designing an evaluation, right? Make sure that what's going on is reasonable. So what about qualitative data? We've talked about things that we can measure with numbers. Qualitative data, usually we capture it either as like a text response that maybe somebody types into a comment box or writes on a piece of paper. We might do an interview with someone and record that interview, and then later we transcribe that. And then we just kind of have these descriptions that people have given us. So what we usually want to do is convert that into something that we can quantify better. And this is pretty intuitive, I think, way of going about this. So usually you establish kind of a coding scheme. So you might have all of these text responses that people gave you about how they felt about your app or something, right? And maybe you just want to say, okay, I'm going to take each statement and I want to decide if it's positive or negative. So that would be like a really basic, or maybe you have a third category that's like, uncertain, neutral or something, right? So that would be kind of the most basic level of doing that. And then what you do is you have multiple people independently look at all of the qualitative data and decide, how to code it. What category does it fit in? And so when you do this with real things, you have a lot more categories, obviously, and you typically have some heuristics or some rules about how you're going to put things in categories. So you'll have several people do that independently, and then you'll check to see how well their categorizations correlate with each other. So in the ideal case, everyone categorizes everything the same way. And so usually what you do is you calculate an agreement value. That's usually a kappa value. And then if there are discrepancies, typically the people who code that data will resolve those discrepancies together. Once you've coded everything, then you've kind of got count data, right? And so you can look at the counts of things. And typically when you code things, you kind of build a hierarchy, right? So you might have like the positive and the negative category, and then under positive you might have like, the aesthetics are positive, or the ergonomics, the feel of it is positive. But you could, look at different levels of that hierarchy when you do your analysis. And you might also look at patterns over time. So if you have someone giving you feedback, as they go through an interface or something, you might see how their evaluation progresses over time. Another way that qualitative data can be presented is just verbatim quotes. And sometimes that's the best way to really communicate how people felt about something. So, some data analysis tools. I've mentioned a few times any kind of spreadsheet software. So Microsoft Excel, Google Sheets, Apple's Numbers, they all will do kind of the basics of quantitative data analysis. Certainly more than enough for any of the evaluations we'll do for like the interfaces we're building for your project or anything like that, where we'll mostly be looking at descriptive statistics. So you probably won't even run a t-test to actually compare things, because you'll probably only evaluate it with a handful of people, and in a lot of cases we'll be looking more at the qualitative feedback, right? What are people telling us about our design? And because it's a small number of people, you can kind of just directly interpret that. But if you do want to do some of the more statistically oriented comparisons, you can do a lot of that in spreadsheet software. As you get into more complicated study designs or bigger data sets, have different needs, you might look at some statistical software packages. So SAS and SPSS are two commercial software packages that have been very popular. And then we talked about R, the programming language R, which is oriented towards statistics and analyzing data, which is free and is great for analyzing things. If you're doing qualitative data analysis, there's quite a bit of specialized software to help you go through and annotate qualitative data. So if you need to transcribe data, I should say. So a lot of times we record audio or audio-video of a participant doing something, and then we actually need to transcribe that into text and then analyze the text. There's a great piece of software called Elon, and it actually will allow you to synchronize, your video, your audio, annotations. You can also put in like sensor data. So if I've got like Microsoft Connect data telling me where somebody's head is looking or if they're nodding their head, things like that, you can sync up all of that on a timeline for your analysis. So that's a great tool for that, and that one's open source and free. So some of the commercial ones, in vivo, MaxQDA, those are oriented towards analyzing qualitative data, and they have lots of features and tools, and they're pretty heavily used in social sciences when qualitative data is analyzed. So, kind of summing up this whole user evaluation workflow. If we kind of want to put it just in steps, right? So basically we design our evaluation protocol. We then bring in participants and we record the data, right? So whether that's adding code to our interface to maybe time how long it takes them to do something, or giving them a survey, or even recording the screen is a great thing to do when people are interacting with your interface, because you can always go back and see kind of the events that happened. Once you've got your data, you'll set it up for analysis. Usually first kind of look at the data and try to do a kind of a common sense check. Make sure there's no weird values just out there throwing things off. Maybe it's a result of somebody typing something in wrong. Then you format your data and you kind of move into an analysis phase with analysis software typically. And that's when you start to create graphs and visuals to see what's going on. And then you interpret those findings. And you might do that with statistical test if you're taking that rigorous approach. Or you might do that by just looking at kind of your visuals and your percentages and your descriptive statistics if you have a small sample and you're using it for quick feedback. So then you'll interpret that and you'll kind of try to explain why did you get those findings, and try to generate as many explanations as you can. So I thought it might be helpful to just go through an example evaluation from start to finish to give you an idea of kind of how this plays out. So I'm gonna use a study, a robotics study that I conducted several years ago. This is the first human-robot interaction study that I ever did, and so I'm going to just kind of walk you through that experience because I think it'll give you some insight into kind of the whole evaluation process. And so I'll be talking about a robot and people interacting with a robot. This applies to human-computer interaction, any kind of human-machine interaction. These same techniques. So this is the picture here is just the paper that's published about this study, but I kind of walk through it, and hopefully this will give you a sense for the whole evaluation process. So we'll start with the problem space. The study is about proxemics, and so proxemics is just this idea of the space around a person. And it turns out that we tend to have preferences and change our behavior depending on if we're interacting with a person, how distant they are from us physically. And so social scientists a long time ago came up, after doing lots of observations with people, these zones, these 4 zones. And so you can see each of them represented here. And then they characterize kind of how people interact with each other within each zone. So what we're going to do is we're going to look at applying this idea to a robot and a person. So specifically, this 3D art here kind of give you a surface level idea. We're going to have this robot that we've talked about before, Survivor Buddy, which is this little piece up here, and it's on top of this other robot, which is called an Inuktun, just a tracked robot that drives forward. And we're going to look at how the robot should change its behavior as it gets closer to a person. Now, you may ask, why is this 3D model person laying down? So we're going to evaluate this in the search and rescue domain. So thinking about this robot being used to interact with someone who's trapped in some kind of scenario where they're trying to be rescued. And we've got a robot that's in there that's found them, and it's going to be communicating with them until they can be rescued. So this is what, when I was an undergrad at Texas A&M, the research lab I worked in, we focused on search and rescue robotics. And so that's kind of how we find ourselves here. But we want to know, we've built this robot that's going to go and hopefully be able to interact with people while they're trapped. And we need to know if it makes a difference how it behaves and as it gets closer to them specifically. So first of all, we've got to have a robotic system. And so you can see here is the top piece there, the Survivor Buddy, I like to call it, that interacts with the person, that sits on top of a robot that drives. Obviously, it's the result of a lot of prototyping. So to give you an idea, we have one here at Mississippi State. Let's see if I can. So I pulled this one out. This is an early prototype of it. So, and it's mounted to just a flat piece for a demo. But it's a monitor. It's got these degrees of freedom, right? Can kind of look around like that. Okay, it can tilt its head, like that. So this is what we're going to be looking at. There's kind of the inside of it. This one is quite a mess right now. But so, Survivor Buddy, it's the nice cleaned up version of it. We're going to look at how it should behave as it gets closer or further from a person that it's interacting with. So we've got to develop some software to do this, right? So the robot does a lot of different things, right? We looked at its joints here. It's got a head, pan, and tilt. It's got this part that goes up and down here. And then this robot on the bottom, it has some headlights on it here. And then it also has some tracks to help it drive, to move forward. So we can kind of think about this as in terms of the robot's behaviors. We're going to have what we call head gaze, which just means the robot looking at the person appropriately. We're going to have a behavior that we call act courteous, which is kind of adapting as we move closer. And then move to goal, which is get close to the person. And we're developing this module that's going to use the distance of how far we are away from the person, and it's going to change all of the robot's behavior based on that. But we need to know how we should change it, right? Okay, so here's some examples of the robot's degrees of freedom. It can do a yes gesture, a no gesture, and here it is on the base from a position where it's high up to where it's lowering down. And so this can be kind of important. People generally don't like you to tower over them too much, especially if they're laying down. So essentially, we're going to take distance and behaviors. We're going to factor that together, and we're going to produce some appropriate behavior for the robot. Won't spend too much time on this, not really important to the evaluation. We conceptualize this as a +1, -1 scale, right? So we have kind of in the middle our neutral behavior, how we would just behave, and then we can either exaggerate that behavior. So if we're nodding our head normally like this, we can really nod it, right? Which people tend to do when somebody's far away. We make our motions are bigger, right? or we can restrict it. If somebody's closer, we can just do a slight nod. So little things like that. But how should we do that? How do we map it? How do we take that distance and decide how big our head nod should be, or how bright the light should be, or how loud the sound should be? We can look at some laws of perception. So when we did sensation and perception, we talked about some of this, how people perceive the world. And so there's kind of this inverse square fall off for a lot of sensation. So like light, the intensity of light falls off with an inverse square. So we also have some other functions that psychologists have given us as they've studied how people perceive the world. Weber-Fechner law and Stevens power law, and you can just see them plotted out here. And it is a factor of stimulus intensity and how that's perceived. Okay. So in our study, what we're going to do is we're going to look at two different mappings. Okay. So first we're going to look at this linear mapping, right? And that's just going to say we're going to anchor the way that we change our behavior as we get closer to the person, and we're going to follow this linear curve. So it's going to be real uniform. As we get closer, everything scales down in a very linear way. On the other hand, we're also going to look at what we're calling a perception-based function, because it kind of combines some of the psychology findings. And with this one, what we're going to do is, as we get closer, we're going to fall off at a different rate, okay? Rather than just uniformly doing this. So that's just that kind of graphed out. Here you go. So this is a better visual of it. If you remember those zones from the little diagram, the little guy standing there, these show you those zones and how we would map the gain. So you can see when we're here, we're far away, right? We're at this exaggerated scale. And when we're very, very close, we're constraining our movements quite a bit. But how we get there is very different, right? Okay. So we've got to plan our evaluation, right? So we've got to decide what we're going to test, how we're going to measure it, how many participants, the protocol. So let's kind of go through that quickly. Okay. So the scenario and the conditions. What we're going to do, we're going to take Survivor Buddy, we're going to put it on top of that robot that moves through the environment, and we're going to do this in a simulated search and rescue environment. So we can't actually collapse buildings on people for the purpose of our study. And we can't necessarily use this on the rare occasion that a building does collapse and we can get to it fast enough and there are people trapped in it that we can find with a robot. We can't really run our studies at that point. So we've got to simulate this. So we're going to create a simulation of this for the participant to experience. And we're going to have our robot approach them from far away, right? From that far away distance all the way up to them. And it's going to verbally interact with them in a way that we would imagine it would interact with them in an actual scenario. And we're going to look at three conditions. So I mentioned linear and the perception-based, which we'll call logarithmic sometimes. But we also need a control condition. And so for the control condition, we're just going to not change our behavior depending, it doesn't matter how close we are to someone. We're just going to do the default, which is, at the time of this study, that's what robots like this would do always. Just default level, no awareness of proximity to a person. So we're going to compare those things. We're going to measure a lot of things. So we're going to have some surveys, some self-report questionnaires. So here's an example of some demographics. We're going to do some personality characteristics in case that has anything to do with how people feel about robots. And we'll do some evaluations, some subjective evaluations of the robot. So those scales where people rate how they felt about the robot after they interact with it. We'll also do an interview with these people. We're going to have some behavioral measures where we measure if they actually take certain actions during the interaction or not. And then we also will have some physiological measures. So we'll keep track of their heart rate, their respiration rate, skin conductance as they progress through this interaction. So here's just a few few pages of some of the surveys that are involved with this study. There are a lot of them, so these are just a couple. So this is after you interact with the robot. These are some of the questions that you would have that the participants answered. So here you can see these are 1 to 7 scales, and they're asking, how friendly was the robot, how human-like was its behavior, things like that. Here are some additional surveys that we conduct. Just these are how strongly do you agree? And then at the end here, you can see some of these are just kind of beliefs that a person might have. So these are things like robots are useful, robots could help the world, robots are a threat. And you can imagine how a person's attitudes and feelings about robots in general might affect the outcome of how they judge the robot. So when we decide on our number of participants, how many people do we need to be in the study? Because it's a scientific study, we need to make sure we can statistically analyze the differences in a reliable way. So we actually do what's called a power analysis. And over here, this is a piece of software called G-Power. And it takes into consideration a lot of these factors about our study, about what we expect might happen, and about how confident we want to be. And it tells us how many people do we need per condition. So we're going to do this as a between subject study. So each person will only experience one version of the robot, either that linear version, that logarithmic version, or the control constant version. And we'll also, I should say, when you do this, you need to take into consideration practical constraints, right? So if it's a really small effect, you will end up needing hundreds of participants, which is not always practical. So you've got to balance that. So once we've decided how many participants we need to write a protocol for our evaluation study. And basically the protocol needs to describe every detail of the study, how it's conducted, and it serves a lot of purposes. Some of the most important purposes, number one, is to keep things consistent. If you've got multiple researchers facilitating the study, they all need to do the same things, measure the same things, behave the same way. It's also going to be needed for ethical reviews. So before the study can be conducted, it's got to be approved. So they need to know exactly what you're going to do in detail. And then it's useful for other people that want to replicate your study, try to get the same result. So just to show you a couple of sample pages of kind of this protocol for this particular study, it's got things in it like, what do you do before a person arrives for the study? And you kind of see all of these very detailed things about what needs to be done for this specific study. And it's even got, down to how do you interact with the participant. You're going to welcome them, then you're going to do the consent phase, you're going to do these pre-questionnaires, and you're going to run the simulation. And it's got, everything you need there to actually run through this study. Another important thing you've got to be prepared for is any kind of unexpected event that might occur during a study. In particular, in a study like this, where you've got people in an environment that's a little bit risky, and you've got physical machinery moving around them. You've got to have a plan in case the participant becomes upset, panicked, if the power goes out in the middle of this, if the equipment fails or catches on fire. You've kind of got to know what you're going to do ahead of time. So that all goes in the protocol. Then once you've got that, you fill out a wonderful IRB, Institutional Review Board application. That's in the United States, what we call our ethics board typically. Other countries have different names for them, but it's generally a group of people that review your study. And they'll go through that protocol, and they will ask you any questions they have. And the whole point is to protect the people that participate in your study. It's really important. Also to ensure their privacy. And this depends on what you're studying as to what safeguards need to be there and what the concerns might be. So you'll do a back and forth with that review board until the study is approved. And then that process continues as you conduct your study. So if anything changes with your study or anything happens out of the ordinary, you do have to work with this review board, this ethics board, to make sure that you maintain the integrity of your study. So that's an important part. One thing that you kind of generate as a result of this process is a consent form. And this, if you've ever participated in a study, you've definitely encountered these. And this is what a person gets before they take part in your study. It tells them a little bit about what they're going to be doing. It will tell them, if they're expected to feel any negative consequences as a result of the study, if they're going to be compensated for the study, how their data will be protected, stored, how they can leave the study. All of those details go in this form, and then they sign it and then participate in the study if they'd like to. So let's talk about now, we've kind of planned everything out, but we've got to actually implement the evaluation. So some evaluations, and this is one of them, are as complicated as the system itself. So in this case, we've got this circumstance where we've got to kind of replicate to a degree we're happy with this search and rescue environment. And so we've got to take on a full design and prototyping approach for the evaluation itself. Okay, so we've prototyped and built the robot that we're going to evaluate, but the evaluation itself has to be built in this case. And during this process, this is the case for anything, even if it's just a software app, right? If you put together a survey, right? Once you put it together, go through it and take it once to make sure that it makes sense, that you didn't make a mistake, that it's logical. So you check for these things. In studies that are, as the degree of complication and detail increases, you need to consider things like training people that are going to conduct the study, and thinking about how much time is the study going to consume. So typically that's a big part of when you ask someone to participate in the study. You tell them it's not going to take more than an hour, and typically the compensation is based on that as well. So the ethical approval will evaluate that to see if it is a reasonable amount of compensation based on the amount of effort the study will take. But you've also got to think about the overhead of between participants. You can't just do it back to back necessarily. So you've got to take all these practical things into consideration. So let's look at the design of this particular study. Okay, so for this we built the simulated disaster site, and here you're seeing it with full lights turned on in the environment. Participants don't see it ever like this, but this gives you an overview of what happens. So the robot starts back here, and then it proceeds towards the participant whose head is laying roughly right down here in this area. And I should say, so everything is blacked out around here with the exception of this area, which has a video projected on at the beginning, and I'll show you that. But the robot's going to move through this area as it interacts with the participant who's confined to this area. So here's kind of a view, and this is again with the lights on, from the participant's perspective of what they see, the robot coming towards them, and kind of the scenario itself. You can see the robot's got right here, this is a laser rangefinder to see how far away it is from the person. So here's that view, we just saw that with the overlay on it. Here's the view towards the person. And so you can see here where these wood blocks are, we put, there's actually a pillow that goes there, so the person lays down in this area. This is a curtained off wall here. So their head will be here, and then this enclosure, there's a cover that goes over it to enclose them in the space. Up here behind the participants, you see here's a projector that's going to project the intro video of this scenario for them. And then here is a bunch of stage lighting that makes the scenario have a more realistic feel to it instead of just having the lights on, and we'll see that. It's a fun study. This is the wizarding area where the people running the study hang out, and you can see there's a lot going on here. Here's physiological sensing system here. Here's the control unit for the robot moving forward through the environment. Here's the main study interface that progresses it through the interaction. Here's video feeds you can toggle through to see what's going on. And oh, here's a spare robot down here. And here's a mannequin head with eye tracking glasses on it, just casually hanging out, as it should be. So here's an example when I say it's an effort to develop kind of this whole simulation in this case. Here is the interface for running through this study as the kind of the wizard or the person who's facilitating it behind the scenes. The robot's not fully autonomous. It's mostly autonomous, where the wizard in this case is just okaying the robot's decisions, so it doesn't do anything crazy, in case we get like a weird sensor value or something. And so you can see that there's a lot here for kind of correcting things or going through these pre-programmed statements. And this is what the robot looks like with the full environment, lighting and everything as it approaches the person. So we've built our environment, we've got it ready to go, we've run it, we can do it reliably. So now we've got to recruit people for our evaluation. So in this case, we've got some beautiful flyers to ask people to sign up to be part of the study. You've got to schedule them, and you've got to actually conduct the study with each person. So I'm going to show you a video now. And this is a video of the study, the participant experience. So first you'll see what participants, oh, here's a question. What did you use to make the environment? Was it just painted wood? So it's a lot of styrofoam and concrete texture patch material, and also like a lot of so like stage broken glass, different kind of prop material that's not dangerous so much, but that looks very realistic. So the scenario is a parking garage collapse. So that's a good question. It was a lot of fun to do. That's why robotics is kind of a good field. But so in this video, you'll first see the participant kind of what they experience as they walk into the lab and go into the study. When they start going into the environment, it will cut to a video, and this is the video that they see once they're laying down in that environment. So I should say, they come in, they can't see that environment, the lights go to a blackout, they can't see anything, they follow glow strips down into the space where they're going to be trapped, they're trapped, and then all they can see is this video play, and then they interact with the robot. So I'll go ahead and play that for you. So this is the video that they're watching once they're in the environment.
Hello. Is anyone there?
Yes?
I can't see you now. I am on my way to help. Please don't attempt to move. You may injure yourself. I am a rescue robot here to help you. Rescuers are now aware you are here and are working to free you. I will be assessing the area and your condition. Could you please tell me your name? Okay, great. First, I'd like to ask you about the building collapse. Please tell me what you remember about the collapse.
I was in the elevator and it just shook and everything went black.
I am relaying this information to the responders. Was anyone with you during the collapse?
No.
All right, thank you. The next question is very important. Please think carefully. Did you see other people on your floor, or were there no other people on your floor?
I didn't see anyone. I was in the elevator.
Thanks. I can't see there is a level sign over there, but I can't read the number on it. Can you tell me what it is?
4.
Okay, thank you. I'm concerned about possible injuries you may have incurred during the collapse. I have an exercise we can complete to determine your cognitive condition. I'll use this information to keep responders updated about your condition. First, how are you feeling?
I'm okay.
Okay, so I will jump out of that for now, since we're getting close to time. So I'll just kind of sum up by saying, once we've done that, we run statistics on kind of all of those measures that we took for everybody in all of the conditions. And then we start to look at if there were differences between the conditions. So here you can just see, this is the gender breakdown by condition, which is kind of these attributes matter to see if there are any effects there. So since we are running short on time, let me jump out of this and we will finish it up next time. But I want to very quickly talk about class next week. As you know, trying to get us to where we can have in-person meetings. So this is the data for the state of Mississippi and for our county specifically in terms of COVID cases. So you can see we are actually flattening out here in Oktibbeha County. That's good news. The state is still a little bit high, but for our campus in particular, you can see that we've kind of come down here, bring us into kind of more recent days. Ideally, where we'd like to be is somewhere below 8%, certainly below 10%, and we'd like to be there for about 2 weeks. We were very close, and then things kind of have started to trend upward a little bit. So I'm going to go ahead for now and say that we will hold our class on Tuesday via WebEx only. Now there will be a few more days worth of data that I'll be able to look at before then. If something changes, if this trend doesn't go where it appears to be going, we will try to get back in the classroom, or get in the classroom on Tuesday. But I would predict that on Tuesday we are just going to be on WebEx. That's what I've got it scheduled as for now. And we'll evaluate at that point for Thursday. Hopefully this is just a little blip in the data, and it will smooth out. But we do want to watch these thresholds. So I will keep you updated on that. For now, please plan to do WebEx only for Tuesday. Things coming up: please complete the quiz if you haven't by midnight. Your project revisions by Sunday on midnight, and homework Tuesday by midnight. If you've got any questions on the project or anything, just shoot me an email, and I will get back to you as quickly as I can. And then please complete the survey if you have specific questions about the prototyping tools, because I'll be working on that this weekend, so that we have a good in detail thing. Question is the survey for Figma and Adobe due by tonight? Yeah, it would be good if you had it in tonight. That is when it's due. If you think of something else on Friday, submit it. But I'm going to start working on it on Friday, so try to get it in by tonight. Attendance is not mandatory. No. So when we have in-person classes, supposing we get to that point, you don't have to be there. It'll just be, I will be broadcasting from that classroom. If you want to come, you can come. But for now, for Tuesday, I won't be in that classroom. So we'll hopefully the trend will be right where it needs to be so that we can maybe get there Thursday. Any other questions before we're finished? Yeah, definitely. Okay, well, thank you, everybody. Like I said, if you have questions, email me. Otherwise, have a great weekend, and I will hang out here for a few minutes if anybody has any other questions. Bye.